Hello everyone and welcome to another lecture in the world of geomorphology. All right, today we're going to be talking about a really important concept in geology, and it's a topic that perhaps unless you've had a class in geomorphology you haven't thought much about, and that is weathering. And so weathering is essentially the conversion of fresh bedrock into bits of broken up, unconsolidated remains. We'll define it here in a second, but essentially that's what we're talking about. We're talking about breaking up rock into smaller and smaller bits of rock and taking our primary minerals within the rock and through chemical reactions converting them into secondary minerals. So that's the weathering process. And when we think about kind of shaping of the surface of the earth, it becomes clear really quickly how important weathering is, right? If we want to think about, let's say a place like Monument Valley in Arizona, we see dramatically different morphology of this bedrock outcrop right here, right? We see that some of the slope is a very steep cliff, which I'm talking about right here, steep cliff up here, and then we have the slopey aspect as well. And so what we're looking at is the differential weathering rates between sandstones and shales. And so on the top, we have rocks that are more resistant to weathering. These sandstones are more resistant, and so they have a greater strength, and they can produce a vertical outcrop, and so it'd be great for climbing on, right? And then we see down below it, we see the shales here are less resistant to weathering. They can break down and form a slope, and so the weathering characteristics of the rock are going to determine the type of landforms we see at the Earth's surface. And we can see some pretty dramatic differences, right, in terms of what hill slopes look like. Here we're looking at Almenakar in southern Spain. There's the Mediterranean out in the distance there. And look at this very steep slope right here, this steep cliff. But it's going to be pretty darn remarkably stable, right, because we have this house that's built right on the margin of this. So this very resistant rock resistant to weathering, isn't breaking down, and it's staying as a solid mass. We can go to other locations and see just nice rolling hills like we see here in Vermont. And so these gentle slopes have different weathering properties from the really steep slopes in Almenakar. And both these landforms can be remarkably stable in the landscape for hundreds to thousands of years. So to understand how these landscapes form and what processes create them, we need to take a step back in geology, in geomorphology, and come back and think about weathering. Okay, so weathering, by definition, weathering is taking fresh rock, fresh minerals, and converting them into unconsolidated remains. Fresh rock, fresh minerals, and then converting them. When we look in the details of what weathering is, the details of what weathering is, we see it's a complex interaction between biologic, chemical, and physical processes that create these unweathered materials. So here we're looking at some really nice unweathered material here. So, some really nice weathered material here. Okay. A term I want to introduce now that we've kind of defined what weathering is the term regolith. And so regolith, when I'm talking about regolith, I'm talking about essentially the products of weathering. It's the unconsolidated materials that cover fresh bedrock. And so here we've got some bedrock down here, and then we have regolith on top. So there's our regolith right there. You might have another term for regolith that you're already using today: dirt. All right, so regolith is just that broken up material. And so this is one type of regolith that's created from the breaking up of local bedrock. But we can also have regolith that's been transported from another location. So here we're looking at regolith from Yellowstone National Park. And we're looking at basically a till deposit on the bottom here. So here's some till, and then on top of the till we have some glacial-fluvial deposits that are slightly more sorted. And these are unconsolidated materials that have been transported from elsewhere and they're sitting on top of bedrock. So we'll still call this regolith. Now notice on the top here, does everyone see at the top of the regolith, we see these dark kind of layers along the top? That's a soil that's forming in the regolith. Now we're going to talk about soils in a little bit of time. After we get through talking about weathering, soils are next. By definition, soils form within our regolith. So we have essentially, by definition, a soil. We're going to have layers within a soil that we call horizons. And those are formed by a complex interaction between the same things that weathering is. We got chemical, physical, and biological processes that essentially create these layers within a soil. And so soils themselves are different than the underlying parent material. So up here, we have soil forming processes that are making layers, and that's different than the unweathered regolith beneath that. But we'll talk about soils in a little bit more detail coming up soon in a couple lectures from now. Okay, so one more thing I want to mention when we're talking about soils, biologic activity is a really important part of soil formation, just like weathering. We can't forget about the biological aspects of it. Okay, another really important term for you guys that you're going to want to have in your head when thinking about weathering is saprolite. Now, a saprolite is when you have intense chemical weathering of bedrock, but the actual bedrock doesn't change in its volume. And so you get intense weathering, you weather away some minerals, but it's still just sitting there. And so here's kind of, does everyone see in the center here? Right here in the center, we've got fresh bedrock. And then if everyone looks down here on the margins, so here going around the margin of this, we have what looks like more reddish material. This is our saprolite, and I can highlight it here. It's essentially deeply chemically weathered bedrock. And how you can identify this in the field, it's really easy. You take a knife, and with saprolite, you can just stick your knife right into it, and it'll go right in. And so that's how weathered it is. You can actually put a blade into the saprolite, whereas if you try to stick a knife in fresh bedrock, right, it's just going to bounce off. So that's no good. Okay, so that's a saprolite. And we can actually have entire clasts of saprolite. So right behind me here, this is what we call a ghost clast. It's a bit of saprolitic bedrock that's actually been incorporated into a river deposit. In this clast, it looks like a regular rock, right? But I could just break it open with my hands, and that's actually what happened. You just crack it open. And so there's been very, very intensive weathering, chemical weathering, that's made that a very, very weak rock. One thing I want to focus on in a little bit more detail here is what this actually looks like. Does everyone notice right up here? Looks like we actually have two colors. Let's zoom in a little bit on that. Oh, look at that. Isn't that interesting? What we're seeing here is a weathering rind. And so weathering generally progresses from the outside of the rock in. On the outside of the rock is where all the moisture is and all the oxygen. And so that's where we can have a lot of chemical reactions. And so we see weathering that progresses into the rock. And so you see more weathered rock along the surface, and then it progresses in. So this would be a weathering rind within the rock. And remember in our geomorphic tools lecture, we actually talked a little bit about weathering rinds. We can actually use this to estimate how long a rock has been, say, in a terrace, right? That because those weathering rinds form when a deposit has been stabilized. So that's a weathering rind. Okay. Another thing I want to mention here is we have biological activity that can enhance weathering. So a term we use is bioturbation. So bioturbation is essentially mixing and breaking up of the fabric of the parent material, of the regolith or the bedrock by biological activity, whether that's tree roots, as we can see here in this picture here, or a tree itself, or that could be ants or pocket gophers or anything like that. All of those would be examples of biological activity. And we're going to take a quick pause here and we'll be right back. Audio check. Okay, and we are back. Sorry about that. I had to get rid of some annotations on the slide from a previous slide, but we're back now talking about bioturbation. I wanted to show you a really cool picture of a type of bioturbation, and that's tree throw. And so tree throw, get my pen out here, tree throw is when we have a tree that's growing, and what happens is the wind blows that tree down, and the roots, which are interlocking in bedrock or regolith, they kind of bring that up with them. And so you end up with a root ball that's full of regolith. Oops. Hold on, sorry, I got to go back now. Get my pen going. There we go. So we have essentially some regolith that's thrown up in the air with the tree roots. We have two root balls right here. The trees were standing here. They get blown over. Here's our other tree here. And it gets blown over. And we end up mixing the soil and breaking up that bedrock. So tree throw would be a great example of biological weathering. So there's a zoom in right here of kind of those rocks that have been kind of pulled up with the root ball. Okay, another great type of biological activity would be ants. So here's some funnel ants, and this is in Australia. And so the ants are kind of, as they're doing what ants do, they churn the soil, they churn the regolith. And so we see here in Australia that actually that upper 30 centimeters of the soil is completely churned over every 200 years just by the activity of ants. So that's pretty cool. Okay, so when we talk about weathering, we generally break weathering into two broad categories, and that's physical weathering and chemical weathering. And so physical weathering is just taking big rocks and making them into smaller rocks. So no chemical reactions here, just breaking from big to small. And so the picture I love to show of this is the Old Man in the Mountain. So the Old Man in the Mountain used to be in New Hampshire. The Old Man in the Mountain is still on the New Hampshire quarter. And essentially there was very significant physical weathering in the large joints in the Old Man in the Mountain, and they tried to put rock bolts in to stop weathering from going further, but they were unable to do that, and so the whole thing collapsed. We had a big rock fall, a mass movement. We'll talk about mass movements a little bit later, but this was essentially frost shattering, which we'll learn about in a second, physical weathering that basically broke apart these rocks. So that would be physical weathering. And opposite of physical weathering would be what we call chemical weathering. And so chemical weathering is decomposition. This is quite different than physical weathering. Physical weathering is just big stuff getting small. And we'll think about kind of what that means in rocks in a minute here. Chemical weathering is when we have primary minerals, whether it's a feldspar, a hornblende, or a quartz grain, and we take those minerals and we actually have chemical reactions that convert them from primary to secondary minerals. And those secondary minerals generally are more stable at the Earth's surface. And so you create these minerals that are stable and stay there. And so chemical weathering. Now, let's say when a granite forms deep under Earth, where you have very, very different environmental conditions. That makes sense, right? Deep under Earth, you're going to have much higher temperature, much greater pressure, and much less water. Okay? And so the minerals that form are stable in that environment. You bring those minerals to the surface, and now they're out of equilibrium. They're in a very different environment. They're in a cooler environment with less pressure and a lot more water. And so because of that, you're able to drive chemical reactions that produce secondary minerals that are stable at the Earth's surface. A class of minerals that are very common as secondary weathering products are what we call clay minerals. So clay minerals are very stable at the Earth's surface, and so we often see those forming. Now the pictures here are kind of showing that a little bit here. So what we're looking at here is on this bottom picture here. This is a photomicrograph. This is a thin section. We've taken a rock and we've sliced it really thin. We've passed light through it, and we're looking at it with a microscope. In these big grains here, does everyone see these big kind of angular things here? Those are primary minerals, quartz and feldspars. And so what's happened is we've seen chemical weathering, and we've seen fracturing of those primary minerals, and then the orangey stuff, all this orangey stuff here, those are secondary minerals that are filling cracks in between the primary minerals. So clay minerals or iron oxides, another form of stable secondary minerals at the Earth's surface. And so those fill in between the primary minerals. So that's chemical weathering right there. And so a landscape like the Badlands is a landscape that's going to be the product of chemical weathering and production of clays, and then kind of how those clays interact with the surface of the earth when you wet and dry them, that we'll learn about here in a second. So chemical weathering. Now, when we think about chemical versus physical weathering, we can think about them in terms of environment and where you're more likely to see them at the Earth's surface. If we break that into temperature, going from cold to hot, and precipitation from dry to wet, we see that when we're in very cold places that are very dry, physical weathering dominates. As we move up in both temperature and in moisture, chemical weathering dominates. And we find a happy medium in between where we have similar rates of chemical and physical weathering. Now, where things are very, very hot, but very, very dry, arid regions, we generally see very little physical or chemical weathering. And then where it's cold and very wet, those are conditions that we don't see at the Earth's surface because you can't get a bunch of moisture into cold air. So that's where we generally see different types of chemical weathering or physical weathering. Now, for the rest of the lecture today, what I want to go through is taking you through some different physical weathering processes that are really important. So the first of those is what we call thermal expansion. And so thermal expansion is a weathering process that happens when you heat up a rock. And what happens is you can heat up the surface of a rock where you have a high heat source. But because rocks have such low conductivity, you can't really get that the whole rock hot. That's really different than metal, right? Like metal, we know metal has high conductivity. You know that you put a pan on the stove, the handle gets hot too. Does that make sense, right? Because of the high conductivity, the whole thing gets hot. If you had a stone pan, you could put the stone right on the flame, and that's going to eventually get hot, but that handle is not going to get hot. Low conductivity. So what happens here is basically you get a heat source, you heat up the rock, the outside gets hot, and it starts to expand. As it starts to expand, the inside is cool, it can't expand, and your rock spalls. And so the outside, where it's expanding, pops off because it basically is moving outward, and the inside can't move, and you break the rock. And so this is what we call spalling, a thermal expansion process. So you do this by intense heat, and then what's the intense heat source? We get a really big flue here in our picture, right? What are these black things here? Those are burned logs. And so where we often see thermal expansion and physical weathering via spalling like this would be associated with forest fires. So let's look at a couple pictures of this. Here's a rhyolitic boulder, and look at this is something we commonly see. See these big kind of dinner plate spalls? This is really common in forest fires. We call these essentially dinner plates as they pop off, and then here's your weathering products here on the margins, and then there's our burned log in the background, evidence of a big forest fire. Here's another spalled granitic boulder, in this case from Yellowstone again. And so those are all parts of the rock that used to be on the rock. And then as the forest fire came through, they were spalled off. Okay, moving on, let's talk about another way that we can physically weather rocks. And that's what we call exfoliation. And so we find exfoliation in places where we expose large amounts of bedrock. And essentially, when we get these big sheets of bedrock, what happens is you essentially will create physical weathering and fractures in essentially layers that are parallel to the surface. And so an individual exfoliation can be anywhere from a couple of centimeters to a couple meters in thickness. So a great place to see these is the Sierra Nevada batholith in the Sierra Nevada mountains in California. And so we've unroofed this pluton from depth, and as you move it to the surface, we get the perfect conditions for exfoliation. So you end up with these essentially these big kind of sheets that break off, very similar in their orientation to the what's exposed, the area of the exposed bedrock. So you're going to watch a video. I'm going to splice this in next, so we're not going to watch it right now, but we're going to watch a video of an actual exfoliation event in physical weathering happening that was caught in real time with a cell phone, and that's going to be from the Twain Harte Dam here, which is in the western side of the Sierra Nevadas. So we'll watch the video now.
Okay. Ho, 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 ho. Ho, ho, ho. Whoa. All the way down. This whole seam now is active again. Lots of activity down below. It's still lifting. Did you see that? It just popped right up.
I felt that one.
Little piece flew into the air. Yeah, baby. Now maybe you'll be happy. Everything is flat again. All those pieces that were lifting just went back down.
For the surface, we still have confining pressure on the sides, but we have no confining pressure over the surface. And so what happens is you set up essentially a differential stress field that is parallel to the surface. And so because of that, you end up with your fractures that parallel that surface. And so as you expose more and more of that batholith, we actually see that we start to see those exfoliation joints that are curving along the sides of that exposed batholith, like we see spectacularly exposed in the Sierra Nevada. So exfoliation joints parallel the surface. Okay, our next physical weathering process is hydration and swelling. So hydration and swelling is when we have clay minerals, those secondary minerals, and those clay minerals, they can actually absorb water when they wet and they expand. And as they expand, they can kind of break out. And so these can be really, really important for things like if your buildings are in a location where you have lots of clay minerals, as the soils expand, you can actually crack foundations. And so they can cause a lot of damage. In a location with lots of clays in a landscape, you can create what's called popcorn weathering, like you see in this bottom picture right here. Popcorn weathering is where you have a rock with lots of clay in it, and then as you wet it, that expands and it expands out, and then as it dries, it contracts, and you end up with these really cool popcorn type morphology, which is really classic of the Badlands. So this is kind of a Badlands morphology, hence the picture in the background here of the Badlands. Okay. All right, let's get on to two more physical weathering processes to finish up with. These involve voids, where we have voids. We have a void in the rock, and we're going to put something in that void. The first one is if we put water in a void, and then we cool that water down and we freeze it, it turns to ice. What happens when you freeze water, especially in a confined location? You probably know this already, right? It's the same thing that happens when you take a can of Coke and you stick it in the freezer. You want to cool it off real quick, but then you forget about it. What happens? You come back and the can's exploded. Now, why is that? That's happened because the water expands and it breaks the can. The same thing happens in rocks. You get water in a void, and then all of a sudden you freeze it, it expands, and it cracks the rock. And so freeze thaw or frost shattering is a really important physical weathering process, especially in alpine environments. And so alpine environments where you have a lot of really cold conditions where you can freeze the rock but then warm it up during the day, that's the perfect location to do this. And so alpine environments are places where you can do this. So look at this landscape here. Everywhere you see are just frost shattered bedrock everywhere. We call this Felsenmeer, a rock sea. And so we get these in alpine locations. Here's some pictures from I should mention that this Felsenmeer here, this is from the top of Mount Washington, the highest point in the White Mountains of New Hampshire. We can go out west and look in the Sangre de Cristo Range and the Rocky Mountains, or over here we've got the South Cascades in Washington, and we see that we have those perfect alpine conditions where we get warm and cold temperatures, and we can do lots of frost shattering. So again, in this example here, imagine this big rock wall here. In the Sangre de Cristo, we basically can warm that up during the day, melt it, and then in the evening we cool it off, and then we fracture a bunch of rock, and then it falls down here, and we end up with steep debris cones at the base of these rock slopes. So frost shattering. Now, it's kind of a little bit of a Goldilocks kind of effect, frost shattering. You've got to have just the right temperature and precipitation. So if we think about this in terms of temperature, from warm on the bottom this time to cold, and rainfall from wet to dry, where we want the perfect conditions for frost shattering are where we have cold temperatures and moderate amounts of precipitation. We need enough so that we can dry the voids out and then wet them again and fill them again. So this is kind of the ideal case. And interestingly, if you get much colder, you actually decrease your ability to do a lot of frost shattering. And that's because when it's too cold, then you don't get those daily cycles when you can freeze and thaw, freeze and thaw, freeze and thaw. Okay, another void weathering process is what we call salt weathering. So this case, what happens is you get water in your void that has ions in it, dissolved material, you evaporate out the water, you precipitate out salts, and those salts grow in the voids and they break apart the rock. This is what we call salt weathering. Two locations where you can do a lot of salt weathering: along coastlines where you have lots of salt, or in deserts where it's really dry, and so you can precipitate out those salts as you evaporate out the water along a bedrock surface. So look at here, these spectacular salt weathering features from the Oregon coast. Everyone see these right here? Just spectacular. Now what happens is we get a bit of a positive feedback loop, is that once you have a little cup here along the coastline, you can get more sea spray in there, and then that evaporates away and you end up doing salt weathering, and then you can kind of you get more and more water, and then you can make these spectacular features. Okay, here's some salt weathering along the Oregon coast again. Notice in this picture here that you have this kind of a consistent line of elevation of where you get the salt weathering. Where you really want to do this is up above high tide, right? Because the perfect place is where you can splash seawater up onto the rocks, but then the water is never going to get washed away. You want to be able to evaporate out that water array. So that's where we see salt weathering really enhanced. It's just above that high tide line. Here's another nice picture here of kind of the morphology of a salt weathered bedrock. Okay, so for both freeze-thaw, aka frost shattering, and salt weathering, you basically have a substance that's growing in a void. So here's some pretty awesome animation. We got a void, and we put some water in there, and we freeze it, and we crack that. Substances grow in the void spaces in the rock. Now where we're going to take this next is thinking about, well, where do these voids come from? How can we make these voids in rock? And we're going to take a little step back, think about the history of geology, history of doing science, to think about some other potential physical weathering processes. All right, thank you very much. That's all I have today about physical weathering. I hope you liked it. We'll be back soon for chemical weathering. All right, see you later. Bye.